a good handle on the last couple of lectures worth of material? Nobody. Awesome. All right. Does anyone want to start with any questions before I go into today's topic? Today's topic is binary exploitation. In a way, it builds on top of reverse engineering of binaries, in that we now have to break them instead of just figure out what they do. This is a rather important part of security because it's you're writing software and you wrote something bad and now somebody can actually exploit it. And to find those bugs, there's a couple different methods. Obviously, there's I have source code, I'm reading somebody's source code, there's a logic error, or they did something bad by design, like they have a backdoor in their product and the password's right there in source code, and boom, I can exploit their software. That's pretty easy. But that's not what happens most of the time. Most of the time you have already made software, like Skyrim, for example, which you downloaded from Steam. And actually Skyrim's a really bad example. Let's do like Destiny 2, which is a modern AAA game that he and I have been playing a lot of. You have a client and you have a server, and they're constantly talking to each other because it's a massively multiplayer online game. And you want to DOS one of your opponents. You just want to get them off of the game so you can win. The way you'd have to do that is you'd have to maybe capture some network traffic using Wireshark and inspect the packets. But it's a custom protocol. You can't understand it, or the traffic's encrypted. So then you have to go a step lower. You have to actually go into the application. You have to first reverse engineer it to figure out how does it work, what is their custom protocol, what is their encryption. If there is encryption, there has to be some point where the data is not encrypted. How do I hook into that and read the data? All that stuff is reverse engineering problems. The exploitation problem comes in you're looking at this and you maybe understand it, and you now need to find a vulnerability in it. That's pwning. That's binary exploitation. I'm going to go real slow, just so we're all on the same page. The tools I'm going to be using are GCC, the compiler, my text editor, Visual Studio Code, Binary Ninja to look at the compiled code. I think I already said my terminal, but yeah. So, feel free to follow along if you have a computer. I'm just going to start by downloading the Hacknight repo. It's going to take a minute because there's a lot of stuff in there. Has MFA on everything now.
You can get MFA on It pulls and pushes?
Yeah, anything that uses my SSH key. Krypton. You should all download Krypton. It's a great tool.
That sounds awful.
It's fantastic.
Anything,
And it also
everything?
signs my commits too. So like, extra security.
That's unnecessary.
I like it. It means I can use one key for everything comfortably. I used to use different keys for everything.
That's what I do.
So, just in case you guys need to catch up, I'm git cloning the HackMate repo. But it is taking forever, so let's just cancel that. So we're going into Pwn, because this is Pwn. And I'm going to make the directory intro Pwn. Cool. I'm going to open this up in my editor. So let's start off with just a simple hello world. I'm going to save this as ex1.c. We're going to include standard IO, stdio, and main. And this will just be a hello world program. Alright, so let's compile that, gcc, ex1, -o, ex1, cool, and we can run it. And is everyone on the same page? Let's introduce a bug. I'm going to make a simple function called win. And it's going to, in an actual challenge, this would be a file read, but I'm not going to worry about that. We're just going to say this is the flag. So cool. I can compile this. This is in Python, in case you were wondering. And I'm also going to go ahead and make a makefile. Cool. Sweet. So now make ex1, ex1. Alright, it doesn't print our flag. That's no surprise, we didn't call the function. But we did include the function in our code, so it includes more than what potentially needs to be there. In a reverse engineering challenge, like, your day is done because you can open up the binary and you can just print the flag. And you can just see the flag there. And I'll prove that to you. So I'm going to go over here and I'm going to use binary ninja. Good? In the back? Cool. Cool. So we see our two functions over here, main, which prints hello world. That's not so hard to see. We see the call to printf, of course, and then it just sort of exits the program. And then we see the win function, which has our flag in it. This is even easier to solve as a reverse engineering challenge because you can just view the strings out of the binary and just ignoring all the built-in stuff, you eventually see the flag. So this is not a reverse, or this is a very simple reverse engineering challenge, but let's turn it into a exploitation challenge. And we're going to do that by saying input. Let's just take some input. So car 100 should be enough. We'll call that input. Anyone confused? Anyone not familiar with C? It's just a character array of 100 characters. So acts as a string. And we'll say, let's print their name. That would just be input. Right?
Hey Kyle, where is that input actually going to be in memory?
We're not going to talk about that yet. We'll get there. Sorry if I'm going slow. Alright, so then if we do, actually hold up. No. Gotta add flavor. There we go. Nope. Nope. What are buttons?
Are you meaning to not write into input?
What was that?
You're not writing into input?
Yeah, we're not writing into input. That is a great point. We will just call gets. That is a very simple way to get input. Jesus. Cool. Now this works. This is a harmless program. Let's compile it again, and let's execute it. Alright, so who am I? Warning, this program uses get, which is unsafe. That's odd. I am Kyle, and it says hello Kyle. So, harmless program. Absolutely nothing wrong with it, except that strange warning. But it does what we want it to do. That's what matters. We don't care about how things work, we just care that they work. That's a software engineering perspective. Let's see. Yeah, I'm happy with this. Let's look at it in Binary Ninja again.
Shameless plug.
And we see in main, obviously there's still the win function, so we're not there yet. But this is a solved reverse engineering challenge. If it was reading from a file, and it was printing the contents of that file to the screen, it's now a exploitation challenge, but that's too complicated to write right now. So we'll pretend that it's a file read. The reason it's an exploitation challenge is because they don't give you the flag file. You need to run it on their server. Alright, so we see the print to hello world. It gets the address pointed there, and then calls printf. First rule of assembly, don't read assembly. Just look at the things that look vaguely familiar. We see oh hello, string, printf again, and in between there we see gets. Alright, that's easy. Binary Ninja makes this even easier. We can go into medium level IL, and it starts to become, I just pressed I twice, starts to look even more familiar. We see the printf call, we see the gets call, and we see the printf call, which mirrors our code somewhat reasonably. We don't really see the creation of the variable because that's done at compile time, not at runtime, but we'll get there. So, let's see. Let's touch on the fact that gets is unsafe. Gets is unsafe. Does anyone know why gets is unsafe? Besides Richie.
Something related to buffer?
Yeah. So, let's test that theory, perhaps. Let's say actually this is the product you make. You don't understand this gets. Your boss is yelling at you, so you don't Google it. You just push it to production. Everything's fine. Everything seems fine. And then suddenly your users start reporting errors. Your program's crashing, your program doesn't work, your company's horrible. Maybe you should have taken that couple of extra minutes and Googled that, but whatever. Let's simulate what maybe the user might have done. Like fall asleep on their keyboard. That's one thing I do a lot, at least. That should be enough. So I'm going to hit enter, and we see that the program aborted. It does print, it still works, but it aborts. If it were a more complicated program, that aborting would have happened somewhere in the middle of your program, and that wouldn't have been good. And then your entire product is messed up. So let's just quickly Google that. Copy, paste.
I think you can man gets too.
Yeah, that works, but why not? Here. Never use gets. It's impossible to tell without knowing the data in advance how many characters gets will read. Because gets will continue to store characters past the end of the buffer, it is extremely dangerous to use. It has been used to break computer security. That's my favorite sentence. Alright, so in the code we said we have 100 characters that we can fill. We call gets, and it will fill more than 100 characters. That's bad. But it's not yet a security vulnerability. Let's pretend that we are in 2012 and we don't have our modern GCC. Let's just add some flags to get to GCC from 2012. And I think I spelled that right.
It's not plural.
It's
just no stack protector.
Thank you. Cool. So security is a thing, and it's become more and more of a thing. So good options are enabled by default. They didn't used to be. Code from 2012 is still very much alive on the internet. So we are still modeling a real world situation. I'm disabling pi because nobody likes pi, and I'm disabling stack protectors, which we actually saw a little bit of already over here. We see this stack guard, stack check fail. So yeah, those are the protections.
What does pi do?
What's what?
What
Oh,
is
pi. Pi is well, what it means is rather complicated. But effectively, if I erase last week's lovely diagram, or 2 weeks ago, or however long, actually, Binja demonstrates this pretty well. So, let's actually, yeah, cool. This is your program. It's just a bunch of bytes. We all know this, I hope. I hope I'm not surprising anyone. It's some length, I don't really care. And if I get out of hex view and stay in linear view, those bytes mean different things. There's these headers at the top of the program, which is this stuff here. Yeah, you're gonna have to believe me on that one. Doesn't show it, but we see something. Come on. Oh, it's not behaving. Cool. We see code. Oh, they changed that. Cool. Yeah, so there's a whole bunch of uninitialized memory. It's all just zeros. Then eventually we get to code with some junk in between it, so on and so forth. You should have seen this in prior weeks.
How is the type Mako different than Elf?
Makos are different than elves because the file format for a binary executable on a Mac is a Mako, and for Linux it's an elf, and for Windows it's a Win32, or just Win. I forget that one actually, but we don't look at Windows binaries too often. What you'll see here is this address range. So __GOT, non-lazy symbol pointers, section started, this address to this address. We can see that it's 1000 to 1010, so it's 16 bytes. And we can see here 1000 and 1008 both have int32 _T, so they're both 8 bytes long, which takes up 16 bytes in total. Your program has tons of these sections. This program has all of these sections. These are their addresses, and these are their names. It tells you a bit about them. Text is code, stubs is code, C strings are strings, data is what it sounds like, data, and then extern is an interesting one worth looking at.
I have a question.
Yes.
When you're done.
Extern is the external symbols we called. So we called printf and we called gets, and both of those are not programs I wrote, so they're external to my program. Alright, what's your question?
When you were looking in Binary Ninja at the segments,
Yes.
the GOT was listed as read-only.
Yes.
So does that mean that GCC was using full railroad protection when you compiled the program? That is to say, relocation read-only to set the GOT to be read-only. Is that right, or is there something else going on here?
This is a different GOT.
Oh.
This is static functions. So this should be read-only because it's the stack guards. Our full GOT. Maybe the lazy pointers? Yeah. So this section. Yep. Cool. The lazy pointers is actually also read-only data, which is interesting. That might make sense though. And that actually contains our GOT stuff.
So by default, GCC was making the lazy pointers read-only. Is that right?
Yeah. But Clang. This is actually Clang. That's why
Oh.
it also looks a bit different than what you're used to seeing with GCC. Similar, but a little bit different. It also uses this instead of a dot table, which is a Mako thing. Yeah.
Okay.
Yeah. You can also see it in Elves, but I think Mako first introduced it. Correct me if I'm wrong, please. Alright, so where were we? Right, we were looking at the symbols, because you asked about the memory mapping. Somebody asked about the memory mapping. This is the first byte of the program, obviously. We're going to index it from 0. But not actually because of security. A program needs to know what addresses it can use. Because if it's jumping to the execution of a function, it needs to know where to jump. x86 solves this in a way because jumps are relative. If you know the distance between you and the function you're calling, you can call that function. But data loading, like strings, is not offset based. If we go look at main and we look for where those strings are stored, here we see that it's actually specifying the entire address. So because of that, we need to know where we're loaded. And if I have two programs running at the same time, and I need to know that information at compile time, which is important. I need to know where I'm loaded at compile time so I can resolve my own memory layout, where I put things. And if I have two programs running at the same time, they can't collide. If I'm running a different program and I request that address, I shouldn't be able to read this program's memory. And the compiler shouldn't have to keep track of where all of your programs are in memory, or you'd have to compile all of your programs before running them, and every program would be mapped to its own space in RAM, and then like you very quickly run out of RAM. So the way that we resolve this is with virtual memory mapping. We say that we're loading ourselves. We say that we're loading this section at 1000 EA0. We say that we're loading this section at 1 something something 4000. And then we let the operating system lie to us, gracefully lie to us, and tell us that whenever we look up an address in this range, it's going to be our address that we allocated in that range. So now two programs simultaneously can have something stored at 4000, but when they each go to look it up, the operating system is going to be like, oh, okay, it's going to use a virtual memory mapping table and say, okay, your program's 4000, that means I need to do your memory mapping, so you're loaded in reality at address F1000, and 4000 relative to the beginning of your program is going to be, let's say it's actually 4000 bytes in, so you're going to do F1000 plus 4000 equals your actual real address. And only in theory the kernel has access to read all of memory, and you can only read your portion of memory that the operating system has allocated for you, which you have asked for. Have I lost anyone?
So is this what pi is?
So what pi is I don't specify these top bytes. I say
We can do it after the...
it's a layer of abstraction deeper. Effectively, instead of saying load me at this address and give me all of these addresses, you're sort of saying, tell me what address I'm loaded at, and then it's not even the program's job. It's the operating system's job. Let's
We can discuss it after the.
it's important though. The disassemblers lie to us because they hide a lot of symbols. A lot of those symbols are called relocations. A relocation is not at compile time, not at execution time. When the operating system reads the program from disk and loads it into RAM, it will replace symbols with their actual values. That's the gist of it. So whenever your operating system reads the program from the disk, PIE means it's going to randomize where it's going to put your program and
In RAM.
replace all those symbols for you.
Okay.
Yeah. The reason for this is so that if I have a exploit that works on an individual address being the same every time, it's no longer going to be the same every time. We did a couple weeks ago, there was a program that asked for an address, and then it read from that address, and it printed it to the screen or something like that. And we were able to go into the program and be like, alright, so the flag's over here. What is this address? This address is a bunch of zeros, F7A. And just print me that address, which has the flag. In a position independent executable, we wouldn't be able to say that because this part of it is going to be random every time, which translates to if a script kiddie is throwing an exploit at 1,000 Windows servers, they're not going to, well, statistically maybe they'll get one or two, but most likely they're not going to get any of them because none of their addresses are the same locally as they actually are on servers. Cool. Alright, so now we've disabled those protections. Let's compile our binary again. I wrote a bad make file, excuse me. Cool, does the same thing, still prints the warning. We sort of are familiar with what this means now, what the warning means at least. But now if we open up our binary again, we no longer see the stack things. Let's just do a side by side real quick. Yeah. This is the old binary. We see the stack guard, stack check fail. This is the new binary. All those protections are gone. So yeah, actually, security means extra code, it means extra run cycles, but it's important for the reason we are about to show. Who here knows about the stack? Oh, actually quite a number of people. Cool. Just to go over it briefly. We've got a portion of memory that saves our variables, saves our state really. As we're executing, we need to know what functions have been called, what the variables were in those functions so we can recover them later. I'm getting ahead of myself. We only have registers here, as you know. So when we go into this function, which is going to use the same set of registers, we need to save those somewhere. That's the stack. The stack has frames. Every function has its own frame because every function has its own set of variables. And so the stack do this into the camera. The stack grows down. It's important. And what I mean by that is if we have OX, my hand is cold. If we have OX 1000 here, and we have OX 0 down here, our stack frames are going to grow down, but when we read memory in increasing byte order. If I read from memory address 1000 and I read 8 bytes, I'm reading 1000, 1001, 1002. And different tools show the stack oriented in different ways. So you have to get familiar with that. Here, you have, of course, you have a stack frame, which is just a section of memory, and then you have what those bytes actually fill. This, I believe, is, this is your high addresses, and then these are your addresses going closer to 0. We can see that from the offsets here. Those are negative. So this diagram is in the reverse of how I normally think of it, which is low addresses on the bottom. So this stack frame looks like, let's see, it shows RDI on the bottom. It shows RSI. It shows the return address, then saved RBP. I'll just say ret and saved. And then we see var, 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 var. So then we have our var. I am going to draw a line here, a line here, and a line here, just to separate out this stuff from this stuff. These are just vars. All right. Everyone comfortable with calling conventions? Anyone have no idea what a calling convention is? All right. So a calling convention is the convention that you use to call functions. When I'm calling printf here, if I use Binge's nice ability of pressing I twice, it shows that printf takes one argument here and two arguments down here. And if I look at the source code, I can verify that. One argument, the string, two arguments, the string and the input. Or the string and the substring, if you want to think about it that way. So in assembly, I don't actually have the way to express arguments to a function at a call instruction. I have to set them up beforehand, and I need some sort of known convention to passing those arguments between functions. And that's a stack. It depends on your operating system and your architecture. It depends on your architecture and your operating system. If we're thinking about 32-bit Linux, basically what you have is you push all your arguments to the stack and then you call the function. So that the function can just pop things off of the stack and it has its arguments. It's really simple, it's really easy, it's really nice. x86, what did I call it over there? We push our saved, RVP, which means RSP gets updated because it points at your current item on the stack. And in the code, it now moves RBP to RSP. So now our BP gets updated. Also, that saved memory is where that was pointing, if that wasn't clear. And now our BP and RSP are pointing at the same thing. So now we're looking at that diagram over there. It turns out I lied to you, and RBP is pointing at your saved RBP and not at your return address. All right. Cool. Yeah. Is that clear? Any questions? Did I lose anyone? Cool. Alright. So then under here, I now have like my scratch space. I can save whatever I want here. So these are all my locals. And RSP points at your current item on the stack. So as you allocate more locals, your stack frame grows, and you safely call the next function because of the move RBP RSP. Because RSP will eventually be down here at an arbitrary address, and it'll use that arbitrary address to build your next stack frame. Because it'll push arguments, save RIP, and then update RBP to point here, and that's your new base. And it has a pointer back. So the stack just keeps growing. But since you have local variables here, your local variables are at a lower address in memory than your arguments. So we're finally starting to come to the interesting part of all of this boring nonsense. Since the stack grows down, you're allocating more memory to lower and lower addresses. But if you write to var1 here, you're writing up, because you're writing to higher addresses. So if I fill up var1, let's say it's 1 byte, if I put an 8 here, and I have a 2 byte number, because, oh god, we're in 1973, it's going to overwrite your saved base address. And now this can get interesting.
So would you call that a short overwrite?
That would be a short overwrite, yeah. Though it depends on your architecture, I'm sorry.
That's true.
Good pun though.
Thank you.
So if I have a buffer allocated to be 100 characters long, and I call gets, which allows me to put any number of characters into that variable, it's going to keep overwriting var1 until it's full, and then it's going to overwrite my saved RBP, my return address, my arguments, my parents' local variables, my parents' saved RBP, my parents' return address, my parents' arguments, as far as your heart desires. And that's the bug. That's the buffer overflow. Because we defined a local buffer, and we have overflowed it with data and written the things about it. Written to the things about it. Alright. So, let me prove this to you. And let's actually exploit this program. So we can call it an A. If I use my favorite programming language, and I say A 100 times, and I find my mouse, I can copy this Control D. I can run EX1. And now I'm going to perfectly fill that buffer. No issue. No issue that it shows. If I do this again, 100, how many bytes do I need to input to get this program to do something or to cause an error? You say 1? You say 1 as well? 5? Do we have more than 5? Going once. No, okay, so 5. Let's do 5. 1, 2, 3, 4, 5. That was more than 5. 1, 2, 3, 4, 5. Not yet. What we have to think about here is 2 things. First of all, enter counts as a character. And we're writing over here, so we're writing over saved RBP. We're not going to see any issues with saved RBP because we're in main. The next thing it does is, like, it has a parent, but it doesn't have a parent. We need to overwrite these 8 bytes because we're in a 64-bit architecture, and then we can overwrite RBP, or the return address. Let me hopefully prove that to you. We're going to say 100 A's. We're going to say 1, 2, 3, 4, 5, 6, 7, 8 B's. And then we're going to do 1, 2, 3, 4, 5, 6, 7, 8 C's. Aww. Alright, finally. CCCC, it might have actually been valid memory. It would be strange. But let's look at why it didn't crash with 16 bytes too much. My input, this is where I'm going to use Midget's nice feature. Get's first argument is RDI. We know that gets is being called with our input buffer, so RDI must be pointing at our input buffer. Let's look back at the assembly. RDI gets assigned the value of var 78. 78 what? Well, 78 hex, but what does that matter? If saved RBP points here, and we are doing, and our local variable is RBP minus 70, we have 70 bytes, yeah, from here to the beginning of our variable.
OX 70, right?
OX 70 bytes, yeah. And OX 70 is not 100. OX 70 is 100 and
12?
12, 16,
106.
64 is 100, 16 minus 4 is 12. Yeah. Yeah?
112.
Python? Cool. So I only gave it, in this instance, 116, so we were still only overwriting RBP, because we need 120 characters to overwrite all of RBP, and then we start getting into the return address. So, even though you might think you have that modeled in your head, and you might know the calling convention for whatever platform you're on, it's not useful to memorize because it changes so much and compilers love to lie to you and not follow convention. So in this case, there was just something extra there. It gave us extra space, probably to account for the enter. but I'm not gonna speculate too much on that.
So that's because the save big pointer was bigger than 8 bytes.
No, it was exactly 8 bytes, but according to Binary Ninja here, RDI, which is the argument to gets, which is the pointer to our buffer, is 0x 70 bytes below our base pointer. We only asked for 100 bytes, but it gave us 0x 70 bytes, which is 12 extra bytes. It's just the compiler being the compiler. Alright, so how do I exploit this? How do I call the win function now? Just speculatively.
Change the return address to win function.
How? What do I need to do? Anyone in the back?
We find out the win function's address, and so after D we put the address.
After what?
So
Oh, after the D's?
yeah.
Yeah. Basically,
Something like that.
the idea is we fill up these 0x 70 bytes, we destroy our saved RBP because we're malforming memory and destroying the program, and then we write our stuff. So we're going to send, let's test this again. We're going to do A. Now, it was 70 plus RBP 8. So this should bring us right up against our return address. So remembering that enter counts as a K, I'm going to hit delete and then enter, and then we see no error. But if I run it again and I do the same number of bytes, this time I'm going to add maybe 2 B's just in case, hit enter, and we get an illegal hardware instruction, which is not one you get to see too often, but it's fun.
What does that mean?
It means that there were bytes at the address we gave it that when the processor tried to decode them, they were not it was not a valid instruction. Instructions in x86 can be anywhere between 1 and 15 bytes long, and not all of them are used. There's a lot of x86 instructions with a lot of different encodings, but not that many. So we fell into one of the gaps. Alright, so our assumption is correct. We now just need to send this program a bunch of bytes to get to the return address, and then the return address we want. So let's do that. We have the win function up here. I'm actually going to save our exploit in a file, and I am going to call it very creatively exploit.py. I'm going to say, hello. No. Alright. A equals, cool, a lot of A's. And actually for clarity, I'll do what we did before. It's going to be A times OX 70 plus 8 yeah, that sounds good. We're going to say our return address is here. So when main exits and tries to return to its sort of existent parent, it's going to return to our win function and instead execute this code. We can say just the first address. We could choose to say one of the consecutive addresses. Yeah. Let's copy that. Does it seem good to everyone? Cool. Cool. Let's run that quickly. Python 3. What did I call you? Exploit. All right. How many characters is this? 1, 2, 3, 4, 5, 6, 7, 10. Is that gonna work? Is our return address 10 bytes long? Is our return address stored in decimal? Unfortunately, it's not. So we need to turn this into something the computer can understand. Let's see. What does the computer understand? I don't know. That looks like a lot of work. Main. For example, if I look at this, these are the actual bytes of this instruction here. In theory, we should see this F97 somewhere. We don't. So how are numbers stored in a program? Well, let's see. Let's look at this call to printf. Printf is at this F54. Well, I already told you that calls are relative, so that's not going to be a surprise. Yeah. Numbers are encoded in some weird way. Anyone have any ideas? No? We should give up. Go home. We're only 15 minutes over here, Richard.
You can sort of see the OX90. The third instruction is subtract OX90 from RSP.
Yeah, I'm not sure about that one.
You can see the 90 there. And then at the third to the last instruction is add OX90 to RSP, and you can see the 90 again.
You are right, actually.
So you can sort of see there's a...
So you can see the 90 here. You can see which 90?
Third instruction from the top.
Oh yeah, you can see the 90 there as well.
And RSP is mentioned at the beginning of that string of the hexadecimal, like the 4881, and then presumably subtract is EC, and then add is C4.
yeah, you're getting there.
There's probably something off about the 4881, but...
Okay, well I'll tell you guys the answer. Who's heard of big endian versus little endian? Nobody? 3 people? Okay. So, for the rest of you, when we have any number, if I have the number 4,312, so 4,312, that's little endian, because my least significant digit is the first one I wrote. This is big endian, 4,312, because the most significant digit, the one that, if it were to change, would have the most impact on the number, is written first. More meaningful to us, at times more meaningful to the computer. What this results in is, if we think of this 90 as a, let me just zoom in. If we think of this 90 as a 64-bit number, because we're in a 64-bit architecture, we know we need 8 bytes. How many hex digits is 8 bytes?
16.
16, thank you. So we see the encoding for this instruction, the physical bytes for this instruction. It's at the 90 is at the end of the instruction. Let's assume it's the end of the bytes as well. So if we count 2, 4, 6, 8 bytes,
That's only 4 bytes, right?
4 bytes. Yeah, that actually makes more sense. That it would be a 32-bit number. So it's a 32-bit number. So it's 8 characters long. And we see this 90 here, which means since the number is really, if you're doing sig figs, because chem, 0, 0, 0, 0, 0, 0, 90, you have the most significant zeros over here, and then your least significant number there. It's not too tricky, but it can really trip you up if you're not thinking about it in the middle of a problem. So what does this mean for our exploit? It means that we need to convert this number into little endian. It's actually not that bad to do it by hand. You can have tools that do it. For the sake of time, I'm not going to teach you a new tool right now, so let's just do it by hand. Boop, 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 boop. That looks weird, I say. That's fine. But it is a 64-bit number. How many bytes do we have there? We have 5. So we need 3 more. 1, 2, 3. So this is the full number as hex digits with something messed around. We know that well, let's just rewrite this. E0, 0E, 0, 0, 0, 0, 0, 1, and then 0, 1, and then 1, 2, 3, 4, 3, just 3. All right. All right, so that should seem right. E0, 0E, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Cool. So we've now made that number little endian. I can comment out that line, save this. Get your flu shot. But we can't print it out as a string. We actually need to encode it as bytes. Thankfully, Python is, Python 2 though. No, I ran this as Python 3. Yeah, cool. We might just be able to say that. Let's try it out. Could not fit int into an indexed sized integer.
We had that function, right? Unhex, it's something like that, hexlimfy something.
Hexlify? Hexlify has some functions. Well, what we could do is,
Why aren't you using Pro Tools?
I'm not going to teach people Pwn tools, it's already 15 minutes over, 20 minutes over.
I mean, you can put it into a string.
I
and
could,
just,
yeah.
Yeah.
So, that. Oh, no, not that. Boop. 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 Cool. And now it's a string already. Anyone who's not familiar, I'm just escaping the hex digits. You can specify any sequence of bytes like this, which is nifty. Now we have to wonder whether or not Python will print it how we want it, and it does. Cool. So let's pipe the output of that into EX1, and we don't get anything. Sadness. Any speculations? I'll show you the exploit again. The number's probably right.
You should
We-
use pipeline.
Oh, that's wrong. Who said that?
You should use pipeline instead.
Oh,
It's
sure.
in there.
Exactly.
Oh yeah. Did you overwrite EX1?
Say that again? Did I overwrite it?
Uh-huh.
Oh, did I make it again?
I mean, when you did the grader, doesn't that overwrite the file?
You are entirely correct.
So you gotta make it again.
Yeah, thank you. It was a combination of things. Alright, so what are we seeing? Right, so I messed up my Linux there for a minute, or Unix in this case. I overwrote EX1 instead of actually put my input into it.
Oh well.
Civil error. And we see, oh hello, fancy string. Segmentation fault, which is not what we wanted. This is going to be because Python 3 is automatically converting our bytes into characters that we don't want them to. They're just not playing nicely with each other. What we can...
Python 2.
Huh?
Just use Python 2.
Yeah, sure. Same problem though. To an extent. I think the solution to this actually might be to use Pwn tools. Or the solution here might be to actually use something that's going to handle the input-output process for us. Because character encodings are hard and people don't like implementing them, but sending bytes over a wire is easy. So Python is trying to, or rather, the terminal is trying to help us out here. The actual character device behind the scenes is trying to be nice, but we don't want it to be nice. We want to be breaking things. So what I was trying to avoid, but we'll have to do, is we're gonna do a import Pwn, and we're gonna say Pwn.process equals so I'm importing a library, pip2 install PWN-tools, or just Google Pwn tools. I am creating the process, so that's not right. So I am telling Pwn to start a process called EX1, assigning that to a variable, and creating our string, and now we just need to send our string. So that's just going to be p.send, and then naturally we want to see the output, so it's going to be p.recv_all.
Do p.interactive and do p.sendLine after. I'm worried that the buffering is going to get fucked up if you don't do
Well, try it out.
receive until.
Oh, yeah, I see what you're saying. Cool. PWN Interactive.
Might want to turn debug on too. Is your address correct?
It's probably not. It's just probably lying to me.
Yeah, I would just copy the address out and just use like U64 or something. Or P64 or whatever.
It's definitely rebasing that for me. Your tools do lie to you. Do know your tools. Load options,
Could the address
Mongo.
have changed when we recompiled the...
What was that?
Could the address have changed when we recompiled it?
Yes.
That's an astounding yes.
No, it didn't change. What I'm worried about though is this might not be the right thing. Ghidra?
Ah, gross.
What?
Ghidra.
You are the one who suggested Ghidra.
When was this?
Like, somebody suggested Ghidra. I heard somebody say copy it out of Ghidra. Alright.
I'm not taking credit for that one.
No, it should be lying to us. But you did say turn on debug.
I would turn on debug, copy the address straight out of Binja, and just P64 it.
Yeah, sure. Debug.
No, dot context. It's poem dot context. Dot log.
Oh.
Log underscore level. Equals debug. Can be uppercase or lowercase. It's a spicy thing to know.
Alright. Cool. So, fits perfectly. Starting local process, that, we can see that we are sending all of those A's, which is 61 in hex, and then we can see that our address got sent. It then also sent a enter after that, because we have the send line, but it's just an enter.
That address correct?
Not necessarily. I'm just we can see that when it's printing this. So that send line is messing us up because it's not null bytes. We need the null bytes.
Well, it's just that's what it's giving back to us. It could like literally just be
Oh, that's
filtering the
also
nulls
true.
out.
I did
Like
put a
that's
new line there.
just the echoed.
Yeah. Oh, don't close. Yeah. Yeah. Right.
Why are you doing OX7? Why are you doing OX70 plus 8?
That's what we saw in here.
You could do it the dumb way and just like literally iterate over, like just guess the offset. That's what I always do.
Welcome to the fun world of binary exploitation. So it's RBP minus 70, and then we want to overwrite RBP, so plus 8.
Why are you overwriting RVP?
Because we need to get to the return address.
Dude, RVP is like if you want to stack pivot. You're just trying to...
The RBP is below the return address.
Yeah.
So we need to overwrite RBP and then overwrite. The plus 8 is RBP.
Oh, I see,
Yeah,
yeah.
yeah.
Is this 32-bit or 64?
This is 64. So let's see. I'll take your address on or advice on the.
That does look correct though, but
It does.
you could also just do symbols. You could load it as a symbol. It's not that big a deal.
P dot.
P64, and then you
Right.
you put the number in. Yeah, just paste the address in.
Let's see if this works. And if this doesn't work, we'll try symbols. And if that doesn't work, there's some voodoo going on. So we are seeing it actually send the same thing, and it's printing back, or yeah, when it's trying to send the message back, this thing, it's printing back the same thing. But we are not seeing us win. One thing I will go ahead and do is say that instead of jumping into the stack stuff, this function setup, I'm going to jump right into the important part here, here, and try that. Because remember, we are obliterating our BP, so we're messing up the stack by default. Yeah, no what? Alright, so symbols. What you want us to do, John?
No, your address is correct. I would just do different offsets.
Oh, you adjust this.
Yeah, like you can throw that whole thing in a loop and like literally just loop over it until you get to the correct offset.
That's no fun.
Okay, you got a different error that time. You got a segv that time. The time before
Yes,
you got
because
it.
we only overwrote our BP.
Okay, yeah, no, that makes sense.
And now, in theory, we're overwriting the thing above RSP.
Why don't you just write the address like 1,000 times?
Yeah, that's, yeah. So we'll say that.
Like, just take out the overflow. Just like write the address 100 times.
Is this a string object?
Yeah, P64 returns a byte string.
So,
Yeah, you can like literally just do times 100 on that. And yeah, just like. Yeah, as long as it's aligned correctly, you're fine.
yeah, that's the next thing. We might be misaligned. We might have to go back to what we originally thought.
Well, you got something else.
Alright, you know what? GDB. If all else fails, GDB. You guys, what? Really? I could have sworn I've debugged things on this before.
That's a conspiracy.
It is a conspiracy. Always have backups, kids.
Idea that we had where you just like literally just the laziest possible way where you just write the address 100 times.
Yeah, since we're having trouble figuring out how to actually, like the exact location in memory, one way you can do things is, instead of filling up a known number of bytes because you're confident in your offset, you can just say that, as long as you're confident in alignment, mod 6 equals 0, or mod 8 equals 0 style, you can just write blocks of memory, like so, and just keep writing up the stack, until eventually you overwrite the thing that you actually want to overwrite. As long as you're not like one byte to the left or to the right, you're fine. Since we are potentially one byte to the left or to the right, we could throw this in a loop and just sort of fuzz it. and try a whole bunch of different things. But I think you guys get the point. It would be cool to see this print, but yeah, we'll have someone else do that next week. Any questions?
How many zeros do you have there? I
How many
you
zeros do I have there? 1, 2, 3, 4, 5.
You just copy pasted that.
Yeah, I copy and pasted it. You know that's the right address.
I'm like pretty sure just something funky's happening with that offset. Like maybe there's something under your buffer on the stack or something. I don't know.
Well, okay, we can re-verify. If we run EX1, or rather, if we run so if we do 64 A's, because our buffer is 100 long, and we add 8 B's for RBP, GDB would be really nice to prove this. There's no way I can get GDB in a timely manner. Oops.
I've got something here that works.
Yeah?
It's the same problem. It was in Pico CTF 2018, and it's the same thing. And I've got the exploit, and it works, and I can just demo
Yeah,
it.
sure, why not?
Okay.
Just a quick demo, just to
Sure.
show you that I'm not completely lying to you.
Right.
Only partially.
I'm gonna plug in just in case my laptop decides to do something untoward. But yeah, so.
We'll need to broadcast.
Oh right. So that's what I display. Usually that just works,
Okay,
right?
yeah, that's good.
That's working? Okay. So, just need to take this and drag it over. Okay.
You make it.
Oh no, it's not mirrored, so I'm going to be doing this a lot. Okay, so here is a vulnerable problem, and it's the same thing.
Oh, yeah.
So here's main, and this part is just saying set you to be the user, and this has to do with when this program is running on the server, they're saying, okay, set you to be the user, and they've got the flag to be something that you can only access as root. So in order to, actually, let's see, I think the way this works is it runs this program as root, so that if you're still the program, then you can access the flag, but otherwise, basically you can't. So in order to cap the flag, you basically have to do it from inside of this program, and that's all that this stuff up here is doing with the GID setting here. So then it just says enter a string, and it calls this vulnerable function, and we've got a buffer of size 32, and then we run gets, and so we fill up that buffer, and just as before, we're going to have a return address and a saved RBP. And I actually don't remember for this problem what the, if this is a 32-bit or a 64-bit application, but we can tell that really easily. So let's see.
Actually, that's what it was. Because we were doing it in main, it's not going to work. Returning from main does a little magic. It uses the ret n function instead of ret.
So
For
if I,
example.
if I just run file on bone, okay, so this is a 32-bit one. So that means that my addresses are going to be 4 bytes long. So let's see, go into exploits. Okay, so buffer 1, and then I've got the exploit over here. These are just some helper functions at the top. This is from earlier before I was using Pwn tools. I've just been kind of learning and working from what I've seen online. So somebody else had a function for basically dealing with endianness. So I can do this pack32 function, which does the same thing as Pwn tools and basically just, well, it looks like in my actual payload I actually didn't use that. So here's my address. And I figured out at some point that the address of the win function is going to be here at 080485CB. And I figured out that I'm going to overflow the buffer, which is 32, and then I've got another 12 A's there, and that brings me right up to the return address. And then I've got this as my new return address. So if I run that, I want to find the window where I have this. Up here. Okay. So this should give me a flag. Okay. Yeah, so what happens is, if you look again at the code here, it gets information. It says, okay, I'm going to jump to this address, jumping to 080485CB. So that's just telling me that when I put in the string backwards to deal with the endianness, that I'm effectively jumping to the right place. And then it goes and calls the win function because that's where it jumps. And so in the code, this vulnerable code, the win function says, open this file flag.txt as read, and then print it. And so that's what happens. I guess I must have a fake flag sitting around somewhere. Maybe it's this flag.txt there. Presumably if I cat that, I should see, let's see, I guess I want to go into where I have the problem. So this should say fake flag, yeah. And of course, run on the server, I would get the actual flag. And so this is just my local test. Yeah, so that's an example, you know, and you can do this and have lots of fun. And yeah, I found the Pico problems are great. I mean, as you can see, this is one that's basically what we were just doing, and it's exactly to just teach you, okay, you know, do opponable, and then they've got a bunch of other ones. Yeah, and it just gets, you know, they just up the difficulty gradually. So like, and they give you the C code. So like for the second one, you want to jump to win, but then it's asking for arguments. So, so it's basically the same problem, except that once you jump here, that's not enough. It checks to see that the arguments that are passed in are the ones they expect. So in this case, you would need to have the return address followed by more information in your buffer that make RDI here be dead beef, and then RSI have dead code in it, and it's the same thing. So, like, I probably have that exploit. I can just show you that. Oops. Yeah, so I've got the return address again, and then I've got 4 bytes. And why is that? what's right above the return address for 4 bytes in 32-bit?
Above higher addresses or lower addresses?
Higher addresses.
Higher addresses are the arguments to the function.
Yes, but the first, for whatever reason, the compiler looks for at basically the return address plus 8 for the first one. So here I've got D, E, A, D, B, E, E, F.
So that is because when you call a function, it's going to push the next instruction's address onto the stack. So it expects basically like what's exactly at RSP to be the next, like the return pointer, and then above that is going to be your first argument and your second argument.
Mm-hmm. But even so, I've got 4 bytes between the return address and the second argument.
Yeah, so that makes sense because you're going to be overwriting your return address.
Mm-hmm.
When you return to that return address, it's going to jump to code that's expecting your RSP is going to be pointed at that EEE.
Mm-hmm.
It's going to be expecting that your arguments are 4 bytes above that and
Okay.
8 bytes above that.
I see. Right. Okay.
It's just an offset thing.
Got it. So since in a 32-bit application, arguments are pushed onto the stack in reverse order, that means that the first thing that gets pushed is the first argument here, D, E, A, D, A, D, C, O, D, E, and then the second argument is this deadbeat. So I think that jives with the vulnerable application, which is expecting arg2. Is that right? First argument? Yeah, first argument, dead beef, second argument, dead code. They're pushed in reverse order. Oh, right, so you first push argument 2, then you push argument 1. So here we've got, that means that when I send in the exploit, I want argument 1 first, there, and then argument 2 higher up, because argument 2 got pushed first. Did that make sense? So it's going to be arg2 up here, and then arg1 right here, in a 32-bit application. So yeah, so that's the same thing, and then I can do that and get the flag again. So yeah, that's all I wanted to show. Any questions on that?
Thank you. So, actually using Linux and using a challenge that was prepared to be exploited instead of prepared in front of you, always a good thing. But either way, you get the idea. I did want to show you the process of how you can create something that's unknowingly vulnerable. I wanted to show you all the ways that your compiler tries to help you and protect you in the modern world. And then, of course, how to actually exploit some older services running at bigger companies and a lot of CTF problems as well. The spirit of it is buffer overflows today. We'll get into more advanced types of binary exploitation where the other speakers will go a bit faster, probably, and have more things prepared ahead of time. So for you guys, all to get ready, you should go to pwnable.kr. Reversing's the one I go to. Pwnable.
That is way too hard for somebody starting off.
Some of the first ones are just buffer overflows.
I would suggest recruit and then.
Well, yeah, the next thing I'm going to say is you should go to recruit and you should do the recruit challenges. You might have to do you have to do any reversing to get the phone
Nope,
now?
it's unlocked just through the intro, just the intro challenge now.
So finish the intro challenges on recruit, then do that. There's also CTF class, OffSec. They have some very low level, easy reversing challenges. If you need the links for that, you can ask me after, or just Google them. What else? There's, I announced it last week, I believe. There's C2, the conference at Seesaw. There's going to be a lot of people who do this sort of thing there. So it's free for students, and you should go, and you should hear professionals who prepared their materials weeks in advance. talk about all those cool things. And I think that's about it. So yeah, thanks for coming today.
One question. So we declared the variables locally, and that's why it resulted the overflow, right? So I just wanted to ask, how do we avoid it?
How do we what?
Avoid it.
How do we avoid it?
Yeah.
You don't use the gets function. You use a function that allows you to specify how many characters to input. So instead of
Okay.
using just gets with the buffer, you use fgets with the buffer and the length.
Yeah.
There are a whole new set of bugs introduced just from that, because what if you have an off by 1? What if you have an off by 10? Off by 10 you could get buffer overflows, but an off by 1, maybe you just control a little bit of behavior. Yeah. I mean, if you want to be very pedantic, you could also pass your buffer in as an argument, so that your buffer is above your return address, so that it only overwrites, well, then you'd be overwriting not your return address, so you're not the problem, but it's the problem of your parent who called you. So like, you know, pick your poison.
It's modern security for you.
Yeah,
Just pass the blame around.
yeah, exactly. Any other questions?
For the point challenges for on recruit, do we
Yeah.
have to complete anything else?
Will you have to complete anything else? You'll only need to complete the intro challenge.
And actually it doesn't
Which
show.
doesn't show, yeah.
Doesn't show them.
No.
Well,
we'll change the
that
challenge.
update hasn't been pushed yet, which
Oh, you're right. It hasn't been pushed. Look tomorrow. Cool. Thanks for coming. There's more pizza.
Thank you.